So today topic is Lenz's law. Lenz's law is a convenient method for determining the direction of an induced current or EMF. And this law is not an independent principle. It can be derived from Faraday law, and it also gives the same result as the sign rules we introduce in connection with Faraday law. It is easy to use Lenz's law, and Lenz law help us to gain initiative understanding of various induction effects and the role of and to understand the role of energy conversion. So Lenz was a Russian scientist who duplicated independently many of the discoveries of Faraday and Henry. And Lenz's law states that the direction of any magnetic induction effect is such as to oppose the cause of the effect. So the cause may be changing flux through a stationary surface due to a varying magnetic field, changing flux due to motion of the conductors that make up the circuit, or any combination. So here let's discuss the very simple approach here. The magnet north pole is approaching towards the loop, and here there is an increase in the magnetic flux through the loop, and that increase induces the current in the loop. And in such a case, the loop also acts as a magnetic dipole with a south and a north pole, and its magnetic moment, dipole moment, is directed from south to north. To oppose the magnetic flux increased by the approaching magnet, the loop's north pole or dipole moment face towards the approaching pole here, so as to repel it. And from the right hand rule, we can find out the current induced, the direction of the current induced in the loop, and which is counterclockwise. Then if we pull this magnet away from a loop, a current again will be induced in the loop. But now the loop have a south pole, this one, facing the retreating north pole of the magnet. So it opposes the retreat, and thus the induced current will be clockwise. So in other words, we can also say that initially, if the magnet is at some distance and and it is not moving, then no magnetic flux passes through the loop. As the north pole of the magnet comes near the loop with its magnetic field, with its magnetic field directed downward, the flux, for example, this is the flux from the magnet. So its magnetic field has a downward direction. The flux through the loop increases when it moves near the loop. So to oppose this increase in flux, the induced current I set up its own induced magnetic field, which is directed upward inside the loop. And then the upward flux of this induced B opposes the increasing downward flux of the field B of the magnet. So, and again, and the current is counterclockwise in such a case. Moreover, the flux of induced magnetic field always oppose the change in the flux of B, this flux, but induced magnetic field is not always opposite B. For example, how we can understand, if we pull the magnet away from the loop, then the magnetic flux is still downward through the loop, but it is now decreasing. Then the flux of B induced must now be downward inside the loop, to oppose that decrease, and here in such a condition the B induced and B are now in the same direction. So this is Lenz's law. Now we will discuss one more case where we will place a conductor in the magnetic field and see the EMF induced in a so in this case we will place a conductor in the magnetic field and we will see how EMF induced in this conductor or in this rectangular loop. So from Lenz's law, we know that whether you move the magnet towards or away from the loop, a magnetic force resists the motion. So requiring your applied force to do some positive work, like in this case, in here, in this situation, or in this case. So at the same time, thermal energy is also produced in the material of the loop because of the material's electrical resistance to the current that is induced by the motion. So when there is a change in magnetic flux, induced EMF produced and induced current is produced, and then there is some resistance in the coil, and there is some energy loss in the system, and that energy loss is in the form of thermal energy, the thermal energy loss. So the energy you transfer to the closed loop plus the magnet system via your applied force end up in a thermal energy. Then if you faster you move the magnet, the more rapidly your applied force does work, and the greater the rate at which your energy is transferred to thermal energy in the loop. And this is the power of the and it is the power, and the power of the transfer is greater. Okay, so how current is induced in a loop? Energy is always transferred to thermal energy during the process because of the electrical resistance of the loop. So if we see this case where switch is closed and a current is briefly induced in the left hand loop, energy is transferred from the battery to the thermal energy in that loop. Then energy is transferred from the battery, like this one. Then here in this condition, this is another situation which in here where induced current is involved. We consider a rectangular loop of wire which has length L and has one end in a uniform external magnetic field that is directed perpendicularly into the plane of the loop. This field may be produced by some large magnet or some other source. So we are going to pull this loop to the right at a constant velocity v. So we can compare it with with this case, or we can compare it with the same case. Here there was also a relative motion, and here it is also a relative motion. In each case, a magnetic field and a conducting loop are in relative motion, and in each case the flux of the field through the loop is changing with time. So so the important thing here is we will go for the arrangement which makes the calculations easy, and this situation makes our calculation easier. So let's calculate the rate at which we do mechanical work when we pull the loop steadily. And we know when we pull the loop at some constant velocity, we apply a force F to the loop because a magnetic force of equal magnitude but opposite direction acts on the loop to oppose us. And then the rate at which we work, this is the power. And power is represented by P is equal to Fv. Fv is the magnitude of the force, and force which we are exerting. So we wish to find an expression for a power in terms of magnitude B, or in terms of the magnetic field, and the characteristic of the loop. So here the characteristic of the loop is its resistance or its length or its dimension, which is L. So when we move the loop towards the right, the portion of its area within the magnetic field decreases, and the flux through the loop also decreases, and according to Faraday law, current is produced in the loop. It is the presence of this current that causes the force that opposes your pull. So to find the current, we first apply Faraday law. When x is the length of the loop, still in the magnetic field, the area of the loop still in the field is L into x. I didn't mention, yes, here this is the x. And we know that magnetic flux is equal to BA, electric flux is equal to EA. Here magnetic flux is equal to BA, and area would be Lx. So this expression becomes BLx. So now when x decrease, the flux decrease. When x increase, the flux increase. The Faraday's law tells us that with this flux decrease, an EMF is induced in the loop. And we can drop the minus sign in the Faraday law, and we use the equation, the magnitude of the EMF using Faraday law would be d phi b over dt. And here this term becomes dl into x, and this one is dx over dt. So the expression for the induced EMF would be bl into v. We replace dx over dt by with v, the speed at which the loop moves. Here this figure shows the loop as a circuit. Induced EMF is represented by E, and it is represented on the left. Collective resistance of the loop is represented by R. On the right, the direction of the induced current is obtained with the help of a right hand rule. And for decreasing flux, if we apply the rule, the current is in the clockwise direction, you can say it must have the same direction as E. So in order to find the induced current, we cannot apply the loop rule for potential differences, which we mostly use in the case of circuit. Here we will only use a simple equation, which is I is equal to E over R, and this equation becomes, by using this value of E, this equation modified into BLV over R pound. So now in this figure there are three segments which carry the current through the magnetic field. Sideways deflecting forces act on those segments, and there is so these are side forces, and we know that the deflecting force would be equal to IL cross B. This one we already studied in the previous chapter, the deflecting force, deflecting force Fd. The deflecting forces acting on the three segment of the loop are marked as F1, F2 and F3. So from the symmetry, the forces F2 and F3 are equal in magnitude and cancel. So this leaves only F1, which is directed opposite the force which we apply on the loop, or we can say force F, and this is the force opposing our pull. So F becomes equal to minus F1. Then to obtain the magnitude of F1, we need to look into the angle, and the angle here is the angle between magnetic field and the length of the vector is for the left segment is 90 degrees. So we can write F to F1 is equal to I L B sine 90 degree is equal to I L D. And now just we need to modify it further by using the value of the current. So this equation will become I B square L square V over R. Here V, L and R are constant. The speed V at which you move the loop is constant if the magnitude of the force you apply to the loop is also constant. So now we can substitute, we can find out the rate of work, and we can substitute this equation here into this one, the initial one, and we would be able to find the power, which is the rate of doing work. So P is equal to Fv, and it becomes B square L square V over R into V, and this expression is modified into R. So to complete our analysis, let's find the rate at which thermal energy appears in the loop when we pull it at some constant speed. So for thermal energy, the power is equal to I square R. So we are just going to put the value of the current here. Here the power will be VLV over, and this becomes B square L square V square over R, which is exactly equal to the rate at which we are doing work on the loop. So the work that we use to pull the loop through the magnetic field appears as a thermal energy in the loop. हाँ बस बंद कर दो।